Hi, Larry Elterman here, and as this thumbnail suggests, I'm going to show you that if you know any two of volts, amps, watts, or resistance, you can figure out the other two. A lot of people don't know that. Of course, electrical engineers know that, but a lot of common lay people don't know that if all you need to know is any two of these values and you can figure out the other two values. So that's what I'm going to show you in this video. And along the way, I'm going to teach you a little bit about Ohm's law and the power equation, and also alleviate some confusion with units, symbols, and properties. So let's talk about who this video is for, who the audience for this video is. So this video is for the informed layman. If you're an electronical engineer, you already know this stuff. But you should know a little bit about electricity, but not too much. If you know about resistance and volts and current and watts, you know what a parallel versus series circuit is, or what AC current versus DC current is. If you know that basic kind of stuff, this video is for you. If you have no idea what I'm talking about, this video might be too advanced for you. So the purpose of this video is as follows. I want to clear up some confusion with properties, units, and symbols. I want to quickly explain the basics of Ohm's law and the power formula. And I want to explain how with any two of amps, volts, ohms, or watts, you can calculate the other two. Okay, so the purpose of this table is to alleviate some confusion about the way people often talk about electricity. People are not consistent in how they talk about electricity. Even electrical engineers are not consistent, and books are not consistent, and there's a confusion, and I'm going to try to alleviate that confusion. So I have 4 properties of electricity, and I'm going to talk about each one. Let's talk about current first. Now, current is the amount of electricity flowing through a wire, and it's usually described in amps. But when you see it in a circuit, sometimes they use the letter A for amps, and sometimes they use the letter I, which is a general letter meaning current, not necessarily amps. But you're familiar with both the term current and you're familiar with the term amp, and it's very common to use both in a sentence. Like you might say, the wire has 10 amps of current running through it. Notice how you're referencing both the electrical property and the unit, which is called amps. Okay, but now let's go to the second table and we'll see that we're not consistent. And here we're talking about volts, but volts is only a unit. Okay, and the electrical property is called electromagnetic force or electrical potential, but the layperson probably hasn't ever heard of these terms. These terms are only terms for physicists and electrical engineers. The layperson only talks about volts, so you never have a sentence that says something like the electromagnetic force of the battery is 12 volts. No, you just say the battery is 12 volts. So the layperson just talks about volts, and they talk about the letter V, which stands for volts. Even though volt is a unit, it's not a property. The property is electromagnetic force, which people don't use. Now let's go to the third row in the table, and we'll see that that's sort of like the first row of the table. We have resistance, which is a common term, and we have ohm, which is a common term. Resistance is the property of electricity. Ohm is a unit. Okay, and in a circuit diagram, we might see R for resistance, or we might see the letter omega for ohm. Now, why don't they use the letter O? Because O could get confused with 0, so they use the letter omega. Okay, and both things are often referenced. Like, it's not uncommon to say something like this: the resistance of this wire is 24 ohms. So we're referencing both the unit and the property. Okay, now notice here you use the letter R. Typically most people use the letter R, even though they could use the letter omega. See, for amps you use the letter A, for volts you use the letter V, but it's not consistent for resistance because people don't like using the letter omega because it's a Greek letter, so they use the letter R, which is not consistent with the first two. Now let's go to the last row, and again we're going to see that the last row is sort of like the volts. We have the unit watt, and watt is a unit of power or radiant flux. Who the hell ever heard of radiant flux? Some people talk about power, but most people just talk about watts. They say a light bulb is rated at 20 watts. They don't say the radiant flux of the light bulb is 20 watts. So the layperson just talks about watts, and it's described by W. So for our purpose, we're going to talk about amps, A, volts, V, the resistance in ohms, R, and the watts, W. Okay, so next I'm going to talk about two electrical laws. And these electrical laws are kind of like the first thing you learn if you're studying electronics or electrical circuits. And the first is called Ohm's Law, and the second is called the Power Law. So let's talk about Ohm's Law first. Ohm's Law says the amps of a circuit, that is the current of a circuit in amps, is equal to the volts divided by the resistance. And that kind of makes sense in an intuitive way, because if we have a lot of volts, which is kind of like the force pushing the electricity, and we have very little resistance, we have a lot of pushing but very little resistance, well, we're going to get a lot of current, a lot of amps. And the power law says that W, the watts, is equal to the volts times the amps. And that sort of makes sense in an intuitive way also, because if we have a lot of push, a lot of V, and we have a lot of current, we're pushing the current with a lot of force, V, then there'll be a lot of watts. And a couple of things to note about these equations. A lot of people, when they try to explain these equations, they use a water analogy, where they talk about the volts as being the pressure of the water, and the resistance as being the size of the pipe, and the amperage as being the amount of water that flows through the pipe. And the thing is, these analogies are kind of good to help you get a general idea, but they don't hold up. So if you try to plug these equations into how water works, you'll find that the equations do not apply to water. They only apply to electricity. So if you really want to understand in depth how these equations work in more than just a superficial way, you really have to study the physics and the electronics of it. There's no free ride. Now, one last thing I'm going to talk about with these two laws is these two laws really become six laws. If you're familiar with high school algebra, you know you can solve, you already have solved for A, you can solve for V, or you can solve for R. And with the power law, you can solve for W, V, or A. So these two laws become six laws as follows. Okay, so on the left, we see how the two laws now become six laws. And now we can use substitution, which is more high school algebra, to come up with six more equations. So these six equations will become 12 equations. Now if you're into math, you can follow my example here, how I use substitution to come up with a brand new equation, okay, which is I have over here. If you're not into math, just let the video skip to the next slide, and you could just assume that I'm telling the truth, which is that these six equations, you can use algebra to now create 12 equations. These 12 equations I am going to show in the next slide, organized in a particular manner. Okay, if you look at the left column of this table, you'll see all the different ways that you can take two properties out of a total of four. We have four, and we're going to take two at a time. So a combination of two out of the original four, there's six different combinations we can have. And these combinations are as follows: amps and resistance, amps and volts, amps and watts, resistance and volts, resistance and watts, and voltage and watts. There is no other combination of two. So if you have any two of the original four, you can look up which two you have in this column of this table, and then you can figure out the other two properties using these two equations. For example, let's suppose you only have the resistance and the volts. Well, then you would go to the fourth row of this table, and you would use this equation to figure out the amps. Amps equals voltage divided by resistance. And you would use this equation to figure out the watts. The watts equals the voltage square divided by resistance. So let's do an example. Okay, so in this example, we assume that you have measured the resistance of a circuit, and it is 6 ohms, and you are using a 12-volt battery. This is all you know, but you would also like to find out how many watts the circuit will use, and also what is the amperage of the circuit. So we can use the fourth row of the table as I showed you before. So the fourth row of the table says amps equals voltage divided by resistance, and watts equals voltage squared divided by resistance. So that means the amps equals 12 volts divided by 6 ohms, and the watts equals 12 volts squared divided by 6 ohms. So the amps equals 2, and the watts equals 24. So I showed you how we can figure out what the amperage is and the wattage is, even though originally we only knew what the volts and the resistance was. Okay, well, that's the end of my video. I hope you enjoyed it, and I hope you learned something. And that's all for now. Signing out. This is Larry Alterman. Have a good day. Bye.